This is part 2 of the 4th demo on PlasMa. I'll be looking under the hood to show how close the language is to the hardware and how elegantly it maps onto machine code. And hopefully you'll appreciate, if you didn't already, like me, the genius of this language. First, the dictionary. Now, this is a linked list containing word names and the code associated with each word. Simple enough. But the surprising thing to me was that the code can be either raw machine code or a list of existing fourth words. Now, this is not too unexpected, given that you can add words to the dictionary at runtime, but it was unusual to see parts of the assembly code looking so similar to higher level fourth code. Here's an example from Jonesforth showing two words called hidden and hide. Now don't worry about what they do, it's just to show the first one is coded as a list of assembler instructions, whereas the second uses a list of fourth words. The Jonesforth uses assembler macros, define code and define word, to simplify defining the dictionary entries. The PlasMa assembler does not support macros, so I had to code them longhand, but the point is still valid. Here's the corresponding PleX code, and just as a reminder, %d starts a data section, %c starts a code section, and %twn starts a text section for word strings, which means one character per word, with no zero terminator. The first item in each entry is an address linking back to the previous entry. You can see the link in hide referring to its predecessor hidden. The next item is the name length. I used an expression here instead of an absolute number, so it remains in step if ever the name changes. The $M means the current memory address, so the assembler calculates the address difference between the start and end of the text name. The overhead of using fourth words here, as opposed to machine code, isn't as bad as it looks, as they are actually code addresses. Each of these names is a label referring to other dictionary entries, such as .hide and .hidden, so there is no name lookup for built-in words. The chains of addresses are also processed using a clever scheme of jump instructions, as opposed to calls and returns, which can have their own overheads. Jonesforth uses the ESI register as the fourth instruction pointer, or IP. This is similar to the machine's instruction pointer, or program counter, PC, but for higher level fourth words. So stepping through a list of words is just a case of incrementing this register and jumping indirectly to its contents. A single x86 instruction, load string, LODSL, is all that's needed to load register EAX with the address indexed by ESI and automatically increment ESI ready for the next word. A second instruction can then jump indirectly to the address in EAX. Now this same snippet of code is used at the end of most built-in words, so Jonesforth uses another assembler macro called next. Now I've used PleX's RB register for this instruction pointer, so my code snippet for next is also two instructions: load R1 with the address indexed by RB and increment RB, then jump to the address indexed by R1. Now moving on to the stacks, the implementation of the two stacks required by Forth, the parameter stack and return stack, depends on your machine architecture. The parameter stack is used to pass values between words, whereas the return stack is used for values from the fourth instruction pointer, so that fourth words can invoke other fourth words and have a way of getting back. The Jonesforth uses register ESP for the parameter stack, which is the same as the x86 machine stack, and this is okay as long as you're careful. It uses register EBP for the return stack. I decided to keep both stacks separate from the machine stack for clarity. This is easy to implement on PleX, as the pre-decrement and post-increment operand modes work for any of the 15 registers. See video 16 on PleX for more details. I've used RC to index the return stack, and RD for the parameter stack, which leaves RE for normal system calls and returns. Here's a quick walkthrough of a couple of words coded in assembler to show the mapping from x86 to PleX. This is the x86 code for the duplicate word. Note the x86 assembler assumes operands are in the order source then destination. So this one copies the item at the top of stack into EAX, then pushes it back onto the parameter stack, which duplicates the item. The normal machine push instruction can be used here as the machine stack is shared with the parameter stack. The next macro was shown earlier and expands to the two instructions load and jump. And here's the PleX equivalent. Note the reversed operand order, destination first, then source, and just one instruction is needed to push the item at the top of the parameter stack back onto the same stack. This is a good example of the power of the QNice instruction set by Bernd Ullmann, on which PleX is based. I believe PDP computer opcodes have similar operand address modes, certainly the PDP-11. The code is then followed by the standard two instructions which jump to the next fourth word. Here's another example using the tick word, which returns the internal address of the next fourth word. The x86 version uses load string again to load EAX with the address indexed by ESI, which is the fourth instruction pointer, and then increments ESI. The address is then pushed onto the parameter stack. The PleX version is able to use a single opcode where both source and destination operands use pre and post options. The more details of the dictionary processing are in the Jones-Forth documentation, where you'll find another feature I had not appreciated. The interpreter is really an interpreter and a compiler, switching between the two modes on the fly. So when a new word is being defined within the colon and semicolon words, it's acting as a compiler to build an entry for the dictionary. And when it's not compiling, it's interpreting or executing words which have already been defined. Now the overhead of scanning the dictionary for matching word names is minimized by doing it once at compile time and planting addresses for the interpreter to use when executing those words. The clever twist on this is that there are other words which can be used to switch to and from interpreter or execution mode within the definition. The final revelation for me was mentioned at the end of the last video. It came about when I noticed that what I thought were core functions of the language, like if, then and else, were defined externally as lists of fourth words. Here's a definition of if, and here's else. Now they use words which we've not covered yet, but don't worry, I'm not going to get bogged down, except to say that those additional words allow access to key parts of the core system, such as primitive code routines and registers like the fourth instruction pointer. There are many other words, such as key for reading a key press, word for extracting a word from the input buffer, whose address is also available as a word, and find for searching the dictionary. Now this is an incredibly powerful feature and means your program can overwrite or redefine almost all of the underlying system on the fly. Also, as we saw right at the start with the example words hidden and hide, any words can be coded into the dictionary before building it. So the particular product called fourth could appear to the programmer as simple or as complex as you like. So I asked before, what exactly is fourth? And it seems to me as if it's not really a language at all, because you can define whatever syntax you want. It's more of a framework or architecture, very minimal in the extreme, but on top of which you can build whatever you like. The introduction in the Jones-Forth S file says it all. Okay, that's enough for now. I hope that's inspired you to take a look, or maybe even a second look, at this intriguing gem of a program from the 70s. And of course, get building a PlasMa machine and relive the experience yourself. Thanks for watching.